But today, it's really great that we have Dr. Christopher Hamilton here to give this talk. Christopher joined LPL in 2014 on the faculty. He got his PhD from the University of Hawaii in 2010, and his research focuses on studies of geological surface processes in order to better understand the Earth, the evolution of Earth and other planets. He's been awarded a NASA Early Career Fellowship Award and a Geological Society of America Early Career Award. And he was also awarded a Fulbright scholarship as well as a faculty fellowship to the University of Iceland. And so he's done a lot of work there that he'll be talking about today during this talk. He particularly specializes in volcanology, particularly like lava flows, the changing nature of volcanoes, magma water interactions, explosive eruptions. So like all this kind of really exciting, dangerous volcano stuff. In studying these topics, he uses a wide range of things. You can see here, drones, field work, he uses modeling, he uses machine learning, a whole range of different techniques, which I'm sure, again, we'll hear about today. And today, the title of his talk is Mars on Earth, Testing Tomorrow's Mars Missions in Iceland. And so I'll hand it over to Chris.
Great, thank you very much. Well, certainly a pleasure to be here, and thank you to everybody who braved that storm to be able to be here tonight, because that was really quite something. It was the most extraordinary weather I've seen since coming to Tucson about 11 years ago. And Lynn, thank you very much for the introduction. And interestingly, I had done my postdoc at Goddard just a couple of doors down from Lynn, and so it was wonderful when he joined our department too. So the great group of folks that are exploration minded. And so that's a focus that you'll see in a lot of the talks with the seminar series here. So we'll return to this image a few times, but I wanted to kind of highlight that on this side, we are actually looking at an image of Mars. That's the surface of Jezero crater. And it's been fused with an image of the highland of Iceland on this side. And so there is a fantastic similarity that we'll see throughout the talk, which really guides why we use Iceland so much as an analog for Mars as well as for the Moon. So going back, oh, no, I do not want to go to this. Oh, this is going to be enough. Okay. So going back to 2021. So this would have been COVID lockdown time. Everybody was very isolated. As Lynn mentioned, I was very fortunate to receive from the US State Department a Fulbright to be able to go to Iceland. It was delayed. I wasn't able to go because of the height of the pandemic during 2020, but I was able to get there just in time for January and for the new year there. And in February, two very different and very exciting things were happening. In Iceland, there was an extraordinary fissure swarm that was happening in the Reykjanes Peninsula with over 40,000 earthquakes heralding the start of a new eruption, which we'll come back to at the end of the talk. That was in those area. And on Mars, on February 18, there was this streaking across the sky above the and that's the Mars 2020 entry, descent and landing vehicle. And so our free video will work. Oh, this is not working. Work during our tests. This one doesn't work, none of them will. So I'm telling them. Okay. So one of the things that makes Mars 2020 such an extraordinary mission is the fact that unlike earlier missions, it's just too big to be able to land on the ground using just a parachute alone. And so earlier on, the Curiosity rover, when it landed in Gale Crater, used a completely different type of technology called the sky crane. And so in a moment, you'll see in this video that the parachute has done the initial aerobraking. In the background, you can see the Jezero fan. And this remarkable thing really does exist. This is the sky crane. And so to be able to land the very heavy payloads on the surface of Mars, you can't do it just with the bouncing balls like they had for Spirit and Opportunity. You need to have a system with a full set of retro rockets, which can then let down on this crane your main vehicle. And so this is almost a SUV-sized vehicle, a nuclear-powered rover, an absolutely fantastic piece of technology. And this is the scary part. It's actually lowering the vehicle down on the ground. Perseverance is now sitting there underneath it. It's an Ingenuity, a helicopter, and the sky crane is disappearing off into the distance to avoid being able to contaminate anything while it's there. And so Jezero Crater is a really exciting area because it's the site of an old lake. There's a delta or fan, which is present in that lake. And one of the real fantastic discoveries right off the bat, which we'll see, is that the crater floor had actually been infilled by volcanic units, but nobody quite knew what to expect just based on the remote sensing data alone. So in this very lonely spot, Perseverance rover was about to start its journey at the same time that I was starting my Fulbright next. So it's very fun. So this is one of my favorite images. I think it could be an image of the century that was taken by a high-rise camera. So they're actually able to slew the spacecraft for the Mars Reconnaissance Orbiter and image this little dot, which is the parachute for the Mars 2020 lander as it's approaching the floor of Jezero Crater. It's in this area, these dark toned units, which we'll see a little bit more, that are volcanic, and this is the fan where a lot of excitement has been in terms of the overall sampling. So in this particular scene, this was taken about a year after landing. There are two things that I'll draw your attention to. The first thing I see is the black stuff in the front, but this is actually the parachute for the landing system, which I was able to see. Now, these black units in the front are, to me, the best type of rocks. They're the volcanic rocks, the igneous rocks. Outside, we have a couple of pieces of large basalt that are very comparable to these types of units. And these have been smoothed over time with wind-blown sand, being able to create these ventifact structures. But the first thing that Mars 2020 was able to do with the Perseverance rover was to be able to visit these volcanic units and begin sampling them. So back in Iceland, this is what the Fagradalsfjall eruption turned into. This is looking at it in August timeframe. And I couldn't stand here, but I flew here. And so outside, you'll see a series of drones. We have thermal remote sensing drones. We have photogrammetric drones and others. And this absolutely wild and wonderful eruption kept me busy. I had a chance to be able to visit it about 80 times during the sabbatical in Fulbright. It was a little bit like at the same time during COVID land. Some of you may have seen my octopus teacher with this free diving and off the coast of South Africa. It kind of felt the same way here. It was like, what would happen if I just went back to the volcano every day that I could? What would happen? What would result from it? So it's really fortunate to be able to do that. So one of the reasons why I'm so interested in volcanoes is that they're pretty, but they're also very interesting environments. This is an example from Hawaii, where the lava is entering into the sea. These actually kind of wild tornadoes being kicked off. But I want to draw your attention to what actually happens when the lava comes in contact with water. And so around, this is for the eruption on the East Rift Zone of Hawaii. This light color is actually produced by cyanobacteria, so basically phytoplankton that are present in the water. And so this is an algal bloom. And these algal blooms can be huge. That little ocean entry is actually feeding a supply of nutrients from nutrient-rich glass into the ocean, and that's able to actually support an entire microbial community, an algal bloom, which is visible in satellite data. So volcanoes and life have a very long history together, and where lava and water come into contact with one another, they're very exciting environments for life. So a student that have been co-advising with Sloanish UML, Nathan Hadland, had this great review paper in Nature. And this shows a variety of different environments where young volcanic terrains can be important for life. We just looked at an example of the algal blooms, but there are also areas where we can have lava-heated groundwater or ground ice that produce ephemeral hydrothermal systems that are also of interest. There are also lava caves and other types of intrusions, many different potentially habitable environments, which make volcanic terrains a very exciting exploration target on Mars. We weren't really expecting one within Jezero Crater. Most of the very young volcanic terrains on Mars are horribly rough, and so very difficult to be able to drive over and have it explored. So this is my favorite part of Mars. It might not look like much from a distance, but I think it's extremely exciting because it has some of the youngest volcanic terrains on Mars. Some of them might be less than 5 million years old, and by some accounts, they could even be 2 million years old, which in terms of overall Mars history is basically yesterday. So this is an example of a large fracture. It's called a fosse, or Cerberus fosse more specifically. And from the Cerberus fosse, you have these very rough lava flows, which have been inundating these old valley networks that were produced by catastrophic floods earlier on. And this is an example from Iceland, from the Holohernes eruption, where we have a young volcanic terrain that was in place in 2014 and 2015, entering into a valley which has a river on the bottom, and all this green stuff in the front is algae. And there are actually other types of bacteria that are present, including thermophiles, which we'll look at a little bit later. But this is what can happen when you have lava flow and placed into an environment with a little bit of water, you heat it up, you provide some nutrients, and all of a sudden it begins to bloom. So this is a bigger picture. This is showing 800 kilometer scale bar here, showing Elysium Planitia. All these lava flows have been placed in this area with the Cerberus fossae 3 unit, less than about 40 million years. Some of these are older, maybe older than 60 million years. And this is the exceptionally young Athabasca Vallis lava, which sources from one of these large fissures. And this is the area that's thought to explore anywhere on Mars. I'd be very excited to, because there's a lot of evidence of lava water interaction, which we know in a terrestrial context is a very good place to be for life. One of the exciting things that also happened, just off the screen here, unfortunately, but right here we had the InSight lander, and this had a seismometer. Then that seismometer was able to detect vibrations or seismic signals which have been generated in the deep parts of Mars. And some of those seismic signals are located directly below the Cerberus fossae. And some studies have actually interpreted those seismic waves as being produced by fluid flow, which is interpreted to be the movement of magma at depth. So not only do we have evidence of very young lava in this part of Mars, we actually have geophysical evidence to suggest that magma may still be located beneath these areas, indicating that another eruption could take place in the future. So my goal, simply stated, is to be able to explore young volcanic terrains on Mars the only way that you really can, and that's with drones. So this little guy, we call him Little Beastie, is actually outside. You can take a look at it, but this accelerates to about 80 kilometers over a span, 80 kilometers an hour over a span of 3 meters, a little bit like a jet fighter taking off an aircraft carrier, and then flies around at about 130 kilometers an hour to be able to collect data. So if you want to be able to send a mission to Mars in the future, how do you do it? Well, you have to have a really great team. So this is our Raven team, and we'll talk a little bit more about that afterwards. Did I see a hand?
Yeah, I was curious, what's the launch mechanism for the
It is a
catapult?
basically glorified bungee cord. So you have a little crank and you crank it all the way up. And then when you release this little pin with the hand launch system, it just fires off. And so it isn't necessarily that high tech. But make sure your fingers are away from it, because when this hand launch system is going, it lever your little fingers. But it's just basically a big bungee cord. So this is our team. This is for the Rover Aerial Vehicle Exploration Network. Everybody with NASA loves acronyms, and so I was very proud of this one. So this is our team. We'll meet them a little bit later. So this is part of a future plan, which to be able to send a science-capable drone to Mars. And so the future for this type of technology would be the Mars Science Helicopter. This would be the next generation after the Ingenuity helicopter, which flew as part of the Mars 2020 mission, but as a technology demonstration. But this larger system would probably be a hexarotor. It's kind of limited by the maximum diameter of the aero braking shell. We saw that in the context of the descent vehicle. And depending on how much you have in terms of your weight, which depends on how many instruments you have, you could probably fly, if you have a nice science-capable payload, for about 6 minutes, which doesn't sound like it's too long. But you can fly a little bit over 10 kilometers with that kind of system. So you can cover a lot of ground very quickly. Yes. You make
The helicopter?
So this is a prototype that was developed in part with JPL and the same company that did the initial design for Ingenuity, which is called AeroVironment. So this has not been built.
Oh.
Yeah, so this is what we would like to send to Mars, building on the heritage of the Ingenuity helicopter, which was full as a technology demonstration with Perseverance as part of the Mars 2020 mission. Yeah. That's a great question, because if you are going to build something like that, you have a very limited amount of mass that you can fly on it. What do you fly? And what type of, not just technologies do you want to be incorporated into the system? So what types of instruments, whether they're cameras or spectrometers or LiDARs or even sampling systems, How do you deal with the science operations, the complexity of trying to run not one, but potentially two different robotic agents in the same time, each competing for the science team's attention, but also the bandwidth that you have available to send the data back to Earth. So one way to be able to test those ideas is to be able to go into the field. It's much less expensive to go to Iceland and be able to try out your technologies. So we had this had been made as an equivalent in terms of its science capability to the Curiosity rover and Gale crater. It doesn't operate with a nuclear power. It has a solar power system. It also has a battery system, but it has all the same types of instruments. It's about a $3.5 million rover from the Canadian Space Agency that they fortunately lent to us to be able to use. And this is a commercial drone. It's a DJI 300, which we can use to simulate some of the capabilities of a future Mars drone. And in fact, in our simulation, it's a little bit of a Hollywood magic. We actually have a fleet of 3 different drones that we were using to simulate different capabilities. Some of those capabilities were samplers with claws and drills. Others were capabilities with regular cameras. And some were also capabilities with things like hyperspectral imagers. Yeah.
What made you choose specifically Iceland to test this on Earth?
Yeah. So there are a couple of reasons. The first is it looks a lot like Mars. And so there are certain things that are different. There's a blue sky and there's a lot more rain. But overall, this combination of very rough, very well-preserved lava flows of similar composition and placement mechanism to what we see on Mars. And then also these sedimentary units, which are another feature. Mars has been eroding for a long period of time. And so a lot of those basaltic materials will erode into basaltic sand. So the combination of young lava flows and these sands, the geological and geomorphological environments very similar. And so it's an excellent place to be able to test a lot of our ideas because the formation of the units is similar and the landscapes are similar. And it's also relatively accessible to get to compared to some other parts of the world. I've also been going there for a very long time. So I did an undergraduate exchange program to Iceland in 2001. And I've gone back every year except 2. And one was this summer. I have 2 little kiddos and it was just too hard to get to Iceland this summer. But it's a spot I've been going back to. And this particular eruption, which started in 2014, I've been studying very extensively. And so it's an area that I'm familiar with. So if you're going to bring a lot of people and a lot of technology to a place, you better know it well. And so those are some of the reasons why we picked this spot. So we're interested in testing UAS scouting, sample retrieval, how we can use the data from the drone and a process called terrain relative navigation to help us identify geological landmarks to be able to navigate by, and also to manage some of the operational complexity of using multiple systems and how to be able to manage shared resources like power and bandwidth. This area, it's near Askja, has been used for over 60 years to be able to help train astronauts and different explorers in different ways. The Apollo astronauts actually began training there now a little bit over 60 years ago, in 1965, and then again in 1967. And they were training in the context of being able to help the astronauts prepare for some of the geology that they might observe on the moon. And many of the astronauts, including Jack Schmidt, trained in Iceland and then supplied that, in his case, to Apollo 17. This is an area that I feel very strongly about. So this is Askja, the Holofernes region is here. So I actually contributed to the UNESCO World Heritage Site proposal to be able to create a World Heritage Site for the Vatnajökull area in the Central Island. And very pleased to say that has been successfully inscribed as a World Heritage Site. And one of the things that we built into that was that we want to keep it pristine to be able to help facilitate analog experiments because it's such a unique and wonderful planetary analog, which wouldn't be that pristine, wonderful place if it were developed in a commercial way. So as part of the overall Moon to Mars program, Earth is actually our first step, not just to be able to build different technologies, but to be able to test them in different contexts. And then we can apply some of those technologies to lunar exploration with the goal of eventually sending not just robotic systems, but human explorers, astronauts to Mars as well. So the key to that whole program is the Artemis program. So the first of the Artemis 1, launched November 15, 2022. The hope is that Artemis 3, which will be the system that brings the next generation of astronauts to the moon, will be in 2026. I would be surprised if it does happen in 2026, but it is getting close. And so the intent there is to be able to explore the South Pole region, the South Polar region of the moon, which bizarrely enough for an airless body does have some ice present in permanently shadowed craters that are very cold and allow those volatiles to rise. These are the types of craters I'm talking about. These are exceptionally dark and very, very cold. And this is a map looking at the South Pole of the moon, showing craters where there's been the identification of hydrogen, which would imply the presence of water. This is what the system could look like. These are flag and some astronauts, crates and such for scale. And in fact, when we were working in Iceland, the joint EVA test team for Artemis was also there at Askja, because it is a great place not just for robots to be able to explore, but also to test certain things. In this case, they were testing the spacesuits for Artemis 3, or at least similar designs that would be then finalized for Artemis 3. Yes.
The water on the surface of the moon, is it the extreme low temperature overcomes the sublimation? It's just surprising to imagine that there's actually water on the surface.
Yeah, it is surprising, but there is water present in these permanently shadowed craters, not just on the moon, but even on Mercury. And so what happens is just the whole kinetics of sublimation slows way, way down when you get to these extremely cold regions where the sublimation process is thwarted by the fact that material, the volatiles are locked as though they would be in rock. So it's the exceptionally cold temperatures that prohibit the sublimation.
How do we know the water's there?
Typically, it's by identification of hydrogen. So there are a number of different ways that you can kick out neutrons from bombarding water. And so while it's permanently shadowed for solar illumination, you can have other types of high energy particles, which can be sourced from galactic regions or other places that impinge, knock into the water, excite the release of a neutron, and you can look at the measurement of the neutrons. There was also a mission which had an impactor that actually went into a permanently shadowed region, followed by a camera to be able to look at the plume that came out from that. And so with that system, they were actually able to confirm the remote sensing detection with another form of remote sensing caused directly by impactor into a permanently shadowed region. So it's really quite conclusive from a variety of different mechanisms that there is water present in these regions. There is some hydrogen elsewhere on the moon, bizarrely enough, but the main concentrations.
Thank you.
So in terms of our overall Moon to Mars idea, these are a fleet of different both landers like InSight, which we talked about, Perseverance, and the little Ingenuity rover, Mars Reconnaissance Orbiter, and other satellites and rovers that are part of the exploration of Mars.
I was curious, I mean, I haven't been to the moon in so long. So how far is our technology advanced that it's just like why go back now? And it's just, I mean, what's the mission, I guess?
Yeah, so that is an excellent question, and there are many different ways to be able to consider the priority for it. But the key area that makes the South Polar region so interesting is that there are certain very high standing mountains, like the Mellowpart Massif and others, that have a continuous line of sight to Earth. And basically, this is the most prime real estate that there is on. And so not only does it have continuous communications with Earth, so you can transmit lots of data, it also has access to water. And so these are the areas that if we are ever in the future going to have a base on the moon, we want to be able to understand its geologic history. And there's also a territorial component that makes it important to be able to establish a claim to those types of areas. So there are many scientific questions we don't know about the moon. Full classes could be taught on the mysteries that still exist there. But in terms of a strategic imperative, there are a number of different countries that are very interested in exploring space, and the moon is going to be an important location. And the most important location, arguably, on the moon is the South Polar region. And so whoever gets there first and plants their flag and has a sustained presence will have basically, like the Gateway program, a very important gateway for being able to explore the rest of the solar system.
Actually, I get that.
Yeah, to be clear, I was wondering, when you said from Moon to Mars, is that also referring to the theory of being able to launch missions to Mars from the moon?
So generally you wouldn't launch directly from the surface of the moon, but there's a region around the moon called cislunar space. And so the future of our space program changes from time to time. But one of the notions was that once we finished getting a foothold in space with the International Space Station in low Earth orbit, that we would move to a more extended space station, which would be the Lunar Gateway in cislunar space. So a lot of the technology for being able to get out would probably use the space station system, but it wouldn't necessarily be launching from the surface of the moon. Some resources might be gathered there, but it's really the cislunar environment that's the staging ground. But also, we don't have a lot of human experience in space on surfaces. There are no people that had been part of the Apollo program 60 years ago that are able to go to Mars. We have to be able to train a whole new generation of folks on how to be able to operate safely in these environments. And so Moon is both an operational gateway, but also in terms of the movement of material from Earth to cislunar space and out. You could bypass cislunar space, but you would need some infrastructure somewhere, the types of vehicles that could bring people to Mars. You can't launch in a single stage. You'd have to do some kind of orbital assembly, either orbit around Earth or orbit around Moon. So going back to the Perseverance rover, so here's our vehicle suspended here was the aeroshell, and then eventually, now that the Perseverance rover is moving down on the sky crane, and it landed there on February 18th. And this is an illustration of what the Jezero crater might have looked like many, many billions of years ago when water was flowing in different parts of the surface of Mars. And in some of these areas where you have the water entering, and I guess it'll probably be entering here and then sitting on that side, you're building deltas. And so the sedimentary record is an important place on Earth. We look for fossils within sediments where they're buried rapidly and then preserved. And so that might be a very good place if we have sediment entering into a lake and providing nutrients with rapid burial to be able to look for evidence of habitable environments, if not evidence of fossil life. So as I mentioned, the first landings, they were exploring in and around this volcanic unit. And the purpose of the mission was to be able to collect samples to be able to eventually return to Earth through a Mars sample return program. This is what those little sample tubes look like. And so these are all little locations where rocks were collected. I'm really excited for a variety of reasons for the sampling of lava, but probably the most important reason is the ability to get radiometric age dating. So we don't really know how old places are on Mars. We use proxies or a different type of data to get at the data we really want. So crater size frequency distributions or the presence of craters, generally if you have more craters, surface is older. But if we can get samples like we have from the moon that allow us to be able to look at the radiogenic isotopes present, we can actually put a real absolute age on those samples to be able to determine our chronology elsewhere. So this is a really exciting area. Basaltic rocks are very good for age dating. And these are some of the samples for that were collected from the Delta. And at the time, Perseverance were hanging out. And overall, Ingenuity made 72 flights, which we'll come back to a little bit later. Quite incredible for a technology demonstration. It was supposed to be. So this is what that volcanic unit looked like. And this is part of the crater rim in the background. If you didn't know better, I could certainly convince myself. I was looking at Askia with some younger lava flows around. These are some ventifacts, so basaltic lava, which has been shaped by blowing wind, also very Iceland-like. And yet another image. The similarities are absolutely breathtaking and frightening. This is a fantastic little Ingenuity rover. So relatively light at around 2.5 kilograms. And it has two counter-rotating blades. It's been around about 3,000 RPMs. And it's able to lift basically a GoPro. And it's a very, very simple camera. It wasn't ever intended to do scientific research. It was intended to be a technology demonstration, but fortunately it had a little camera on it. And this little sidekick is solar powered. It would kind of sit here, trickle charge, and when it was ready, it would do a series of test flights. And as I mentioned, it did 72 overall. And it was supposed to do those 5 flights in a 30-day mission. Actually spent almost 3 years exploring the Jezero crater region, over 1,000 Earth days, being able to travel around and demonstrate that flight is possible on Mars, despite it having very thin atmosphere, about 180 atmosphere pressure. So we'll see if this works. Yes, maybe. I'm gonna click on my computer. Oh, oh, doesn't go at all. All right, back. All right. So that's now some of these landmarks we might be getting familiar. So this is our basically landing environment, and it starts doing its 5 little flights around there and becomes bolder and more brazen, flying all the way over and even making it to and onto the delta. And so each one of these little flight legs, we're gaining experience about how to be able to fly on Mars. It's able to explore all these different areas, and eventually just keeps going. And once we get into the 70s, you'll see that there starts to be a bit of an issue. Sand. We don't like sand. Because one of the ways in which the rover operates is it uses certain types of technology like cameras and odometry, but it doesn't ever really run the risk of falling. It could get stuck. But when the Ingenuity is trying to land, it has to be able to use its camera systems, and it has one very simple laser ranger to be able to figure out where to be able to land. It uses this terrain relative navigation system, very simple version of it. But the trouble is when you have very, very smooth terrain, very featureless terrain, it's very hard to know how close you are because the surface is self-similar. And so unfortunately, what ended up getting the Ingenuity in the end was very mundane. It was a landing on a featureless surface and it didn't quite stick the landing. But 72 flights is fantastic. In fact, it was so great that at the time Congress said, we want more of these, make me 2 more. We want to be able to collect our little sample tubes on the surface of Mars using drones and to be able to bring them into our sample retrieval lander and shoot them back up into space so that we could then get them to an orbiting vehicle and bring them all the way back to Earth to be able to use fantastic labs like we have here at LPL to study the characteristics of these rocks in conditions with much more sophisticated instrument than you could put onto a rover. Well, how do we test to see if this is possible? Well, we can go and do certain experiments in a Mars yard. JPL has one, many places do. We have a little Mars yard outside here. Or you can go to a place that looks just like Jezero Crater. So this is the Hollerhorn region of Iceland, and this is Jezero Crater, and this is our Mars exploration rover, the Canadian Space Agency's equivalent of Curiosity. And this is a little mock-up of what our little drone could look like. And so we want to go from this type of mock-up to actually testing some of the technologies, including samplers with claws and drills and all sorts of others. So to be able to go to a place like these young volcanic terrains or these volcanic terrains in general, the Hollerhorn region is excellent. This is wintry, so we don't go then. We go in the summer when it's all nice and relatively dry. One of the reasons why I'm particularly interested, the vents hanging out here, that's we just looked at in the previous image, but when the lava was entering into the Jokosala River, it began to interact with the water and produced all this fantastic steam, which is coming out, as well as hot springs in the front. So this is the river system. This is where the lava flow was in place. And this is the example of the green algae-rich environment in front of the lava. And so we did many different things there, including sticking a bunch of thermocouples into all the streams. We had to look at how the temperature changed both in the lava and in the surrounding water. Shown here in black, this is the atmospheric temperature. So you're basically looking at daily cycles, temperature fluctuation. And in this section, there's really no elevation in terms of the water temperature. And then here we start getting these spikes with relatively hot water. In some cases, this was almost 17 degrees. In the first year, not only is there steam coming out, which implies that it's boiling, the hot springs were over 40 degrees Celsius. It just took us a while to get our funding and our instruments to be able to go back out. And then over here, we have relatively little variation. And the key to being able to understand these water temperature variations was actually looking at the water height through the stream system. So each day, the glacier melts a little bit and some of that water, the diurnal floods come through. And as the water comes in and rises, it interacts with the hot core of the lava. And then the hot springs, which are produced at the flow front, then carry enough heat to be able to be exciting from a biological perspective. So this is what one of our drone mosaics of that hot spring system. This is some of the glacial river water. So it's all filled with glacial flour, which is not flour at all. It's just very finely grained sediment that's been ground down by the glacier. And these very bright blue areas, those are filtered water that's gone through the lava and is emerging relatively hot. So we sampled all these different streams to be able to understand what was there. And this is a little bit of a busy spot, but the key thing here is that the glacier river, number 8 here, you can see that has very little in the way of biological diversity. So we're measuring the biological diversity using R16S sequencing to be able to locate the different types of microbial organisms there. We filter out all the eukaryotes and really just care about the bacteria. And then when we get to these lava heated streams, you'll see these yellow zones. And those yellow zones are actually a type of thermocline bacteria. So here's an area that's generally very cold, and you just add heat, and all of a sudden that hot water is able to be colonized by microbes that maybe have been sitting there for a long period of time. So certain types of organisms can be very durable for long periods of time by entering into what's called a cyst. And certain types of things like salt, which is precipitated through hydrothermal systems, can form a little shell around these microbes. And then afterwards, when you begin to have lava heated conditions where it's nice and warm and wet, you can reanimate them. And so there are some studies that are questioned, but people have potentially been able to reanimate microbes as old as 250 million years, but certainly things on the order of tens of thousands of years, even millions of years. There's certain types of microbes that can enter into dormancy. And if conditions are right, the next lava flow unit comes in, you could potentially have those types of organisms there. So there are different types of things that are also present here. So different types of bacteria, but the key ones that are particularly interesting here are the black boxes. So in terms of being able to explore volcanic terrains, I don't want to go into this in too much detail, but I do want to introduce a touch of jargon, and that is that we have relatively smooth lava that's called ahoy hoy, and we have relatively rough lava that's called aa. They are formed under different shear strain rate conditions and have different viscosities. But the key thing here is that you have a continuous stretching balloon-like carapace. And in these cases, the shear strain rates are so high that you're tearing apart or brecciating the lava surface to be able to produce an clinker. As with anything, if you look at it in a little bit more depth, you can find all sorts of other cases. And so I'm generally interested in these so-called transitional lava flow types. And the reason why we want to be able to understand them is they tell us different things about the eruption process, but in the process of exploring different environments, they tell us what to expect if we're going to send a lander, if we're going to send a drone, if we're going to send a rover, and what types of surfaces to expect. We can traverse easily on foot and even land a drone on platy surfaces, but you cannot land on or rubbly or certainly not the slabby. So how do you identify them? It's an important thing. So the Holoherrin eruption gives us an opportunity to study these surface types in relation to emplacement processes because it happened recently, just basically a little over 10 years ago. It was very well studied. So we've made some fantastic maps. This is one from a graduate student, professor at the University of California, Riverside. And she made a fantastic map of all the different lava flow textures that are there. So the key thing here is they're all basically transitional lava. And we wanted to conduct our field observations using our simulated mission right here, where we have some lava flows that are directly flowing over sand. And this is a nice accessible area that allows us to be able to test our different technologies. So this is our Mars Exploration Science Rover, MESR. And if I don't talk too much about the rover and focus mainly on the drones, it's because I'm a drone guy. I prefer flying around than driving around. So this was one of our vehicles. This is Ravenclaw. We had some folks that liked Harry Potter quite a bit. And we wanted to try different types of scoops to be able to see whether or not we could pick up different types of materials using a drone. And this is one of our little claws. And this is a 3D printed version of this the same sample tubes that Perseverance is dropping on the ground. And so we were able to fly it around, around a little bit. Do a Pac-Man and crunch onto it. Pretty soon we'll kick back up the rotors. And make off with our tube. So it is possible after all. Now, there's certainly different types of things you could use, like better terrain route navigation. We actually were manually plotting this one. And I will say we tried a lot before we got one that worked too well, because it's actually very hard to land with that. It's a little bit like one of those circus claw things that you might use, because you have to kind of see from a few different positions. In the line of sight, it can be hard to see where you are. But this is really just a computer vision problem. The fact that we can do it and the technology works is kind of the key focus. We also built another system which uses a drill. And so we're able to drill different types of materials, which opens up a whole new category of sampling to be able to do from a drone-based platform. The results for this we're still working on. There's still 3 more papers to go. We've finished 6 so far. We have a special issue in the Planetary Science Journal, the Planetary Analogs for Solar System Exploration, results from the Raven mission. We have 1 paper about simulating the science operations of a joint rover helicopter mission architecture in the Mars analog setting, unoccupied aircraft systems for sampling on Earth and Mars. There were some questions about why Iceland. We have a whole paper here talking about why Hollerhorn is such a great volcanic analog for Mars. High parameter, that's a paper by Michael Phillips, a fellow here, research scientist, looking at some tools for hyperspectral remote sensing. Evaluating the use of unoccupied aircraft systems for planetary exploration, and comparing rover and helicopter planetary mission architectures. So this is how we build up the information about different types of technologies, the science and the science operations that will allow us to be able to make future Mars missions more successful and incorporate next generation drone technology. So the questions are great. I might not get to a certain final section, but I often put a little part that I can cut. So we've got a few more minutes. So I'll highlight a couple of extra things. But the last few slides, you'll have to forgive me. We'll have to skip over for the sake of time. So this is our Raven team, which we introduced before. This is our little science village. So we have our little solar powered system and our big shipping container. We brought everything out, all of our little kits. This is where we have a biological sampling station. We have other stations that are built with being able to do the mission planning. Because in the field, we were actually designing our exploration strategy, coding it all up using a system called UGCS, Universal Ground Control Station, then flying it. So we were simulating all the different parts in terms of energy consumption, in terms of bandwidth, in terms of mission planning you would have with a real mission. Yes. This was about 3 weeks. Yeah. I went out earlier to be able to set stuff up, and so it probably for 5 weeks. But it's expensive to bring out a lot of folks, and we want to have everything ready. This is Gudrun, our cook, to be able to make sure everybody was well fed too. But we were trying to simulate 10 Mars days or sols for the rover and for the drone. And so we were actually, in this case, running 2 parallel missions. So we had 2 full science teams, 2 full everything that we were running in parallel. But we have to budget in this area. There was a question about how similar this area is to Mars. Well, it looks similar on a good day, but it rains and it has terrible weather. And so we have to plan for about 50% weather scripts. So that's why we were there for about 3 weeks to be able to execute 10 days of simulation. This is part of the logistics to set up first. This is our IMSCIP truck, side loading vehicle. Our rover is hanging out in there. We actually had that custom made in Toronto by a company that does yachts. They do fiberglass yachts. It's very fancy racing ships and stuff, sailing ships. Fortunately, they were excited by the project and it wasn't very expensive to be able to make. This is a full fiberglass hut. We tried a lot of different designs and basically in the end, mostly doghouse. But these two, the top pops off and then the 2 sides clip together. You can clamp it down on the ground and you can deal with some serious winds. So it's designed to be able to deal with. We also had to work with the local power company, the telecommunications company, Nova, to be able to get high bandwidth communications through a series of microwave relays, because some of the folks from JPL couldn't come out for 3 weeks. So we actually had to have data transmission in a place with no internet connection all the way back to Pasadena. This is our Mars Science rover. Now, unfortunately, one thing you might notice is it doesn't have an arm. There's no robotic arm. And so that got plundered by the Canadian Space Agency to be able to put on a different rover that they use for lunar operations. And so instead, behind the scenes, we have a bunch of tripods. And so we have all the different instruments that would be on the arm being used manually, but following the same rules that you would use in terms of you need to be able to first go to the location, you have to image it, then you do your fine corrections, and there's a whole sequence that we had to be able to do to be able to say, if we're going to make this measurement, what are the things we have to do first? Because each one of those targeting commands takes bandwidth, it takes time, and they have to be done in sequence. So when we get to a particular place, each person has a role where they're simulating. We do have a fully autonomous rover using stereo vision and LiDAR, but some of the other types of instruments, especially the hyperspectral imaging and other types of data we were doing manually. But otherwise, it's going around and exploring this environment using a nice plan. We needed to be very careful that nobody could really see or understand the environment using anthropogenic cues. And so every time that the drone was flying around, we had to make sure that we put the rover in the doghouse because none of the team actually had any idea how big that little marshmallow was. It could be big, it could be small, but it didn't give them any clue as to the size of the feature. We actually executed not 10, but 12 sols. We flew 10 kilometers, surveyed about 70,000 square kilometers, acquired 86 images. We could have acquired thousands, tens of thousands of images, but we were limited by the bandwidth that would be realistic if you were relaying that data through something like Mars Odyssey or through Mars Reconnaissance Orbiter. Bandwidth is actually our key limitation. Our goal was to be able to do at least 3 samples. We picked to do 1 on sand and 2 on lava. We used laser-induced breakdown spectrometry to be able to make certain types of measurements and also used a visible infrared point spectrometer radiation. So we tried a whole series of different instruments. Overall, during that 10-day mission, the rover was able to start here and go there. And basically, the drone can run circles around them. So we were limited to the same kind of constraint of 6 minutes of flight. It's actually power requirements, so it is a total of 6 minutes, but they were able to jog up here, do a little bit of data collection, all these grid flights or to do photogrammetry, fly all the way down, image the surface, land on this lava, actually, sampling from the lava. And then we were radiating all of our samples back to this cache location that we could then, if it were a real mission, be able to collect the samples from afterwards. So that little drone can pick up 1 sample at a time and collect a full Rosetta like a rover could. This is our geologic map, which we'd made before we went into the area that was sort of guiding the different geologic units we want to be able to visit. So we nailed all of them during that time period. These are some of the images that you have from the drone, and without any anthropogenic cues, it can be really difficult to see what the scale would be. And in fact, that's one of the key things that we recommend in terms of future technologies is something like a LiDAR system that gives you ranging so that you can assign scales more reasonably to these different targets. These are some of the lava flow features, and this is actually an image. This is a place you would not land. This is an area you would land, and this is what it looked like when we actually got onto the surface and were able to sample some of these little sulfur-rich and gypsum-rich fumarolic deposits on the surface. This is an example of what the area would look like with the data scaled to high-rise scale. So it's high-rise is 26 centimeters per pixel. And it's like putting on your glasses of the eye doctor. This is what it would look like and did look like with 1 centimeter per pixel data collected from the rock. So it gives you a lot more detailed work. Not only does it give you visible images, but you can use stereo photogrammetry to make different train models. So this is what the equivalent 1 meter per pixel high-rise derived digital train models would look like. And this is what the train looks like when you have the topography, in this case, that hillshade from the drone derived data. And this was an example of our scoop being able to pick up sediment material, and it's actually able to transport it in there. It seals quite well. There are improvements you could do to the design. We tested 4 different scoop designs of different types. Yeah, okay. We've got a good stopping point coming up. So this is the photogrammetric process. So you can fly a drone and collect overlapping images. And just like we derive stereo from having parallax between our eyes, you can do the same thing with drone derived data. But you can also use a LiDAR system to just get the data, elevation data right away by using light detection and ranging. We've used that type of system in a variety of different contexts, including cave systems to be able to explore. And our hope, we did a discovery mission concept called Moondiver to be able to explore lunar lava tubes, and a different project, which is using the Ouster OS1 LiDAR system, commercial vendor, to try and make a simultaneous localization and mapping LiDAR system for future lunar exploration and hopefully also for Mars exploration. So this is our moon context. And in fact, when we were in the field, we were working with another group from the Marshall Space Flight Center. It's another space flight center in Huntsville, Alabama. And this little cute little drone, much smaller than our other one, is being navigated exclusively using LiDAR from Huntsville, Alabama. So that we're actually in real time sending the data back. All the controls were actually being done from on the ground. And it's that type of LiDAR technology that lets you see in the dark if you want to be able to explore a place like a shadow. As I mentioned, and I won't have time to go through too much here, but as I mentioned in the very beginning, back in February 2021, there were these earthquakes taking place. Reykjavik's up here, Keflavik Airport's over there. And this part of the southern section of the Reykjanes Peninsula, there are all these earthquakes, 40,000 of them. And so because we thought an eruption would be imminent, we were able to get funding from both the University of Arizona, the RII, the Research Innovation Impact, that's what it was called at the time, and also from the rapid program through the NSF to be able to bring folks out. It got lots of different attention. I had a chance to meet Anderson Cooper at least virtually as part of this process. We have a Netflix volcano special. It's called Earth Storm. And so episode 2 is that we deal with different types of volcanoes of different magnitudes. And we have one section on Sept. This is part of the team that we were able to bring out. This team is L for lava, A for Christopher, and P for Nathan, and A for Brett Carr. So we all love lava a lot. It's erupting quite happily in 2022. This is Solange. She'll be giving a presentation. The next one is for Jack, and we actually tried his ground penetrating radar drone in this area. Solange is in molecular and cellular biology, and so she's been doing all of the work with Nathan to be able to characterize the biology of these systems. We wanted to see how young lava was actually colonized by different microbes. Madison Tui, who's in geosciences, PhD student working with us as well. And I really like Rollo. He's my truck. Very muddy, but we wouldn't have been able to get anywhere without our trucks with nice 36-inch wheels. And so I'll leave with this if it works. I'm going to try clicking. Because everybody you just saw also likes drones. And so if we want to explore Mars in the future, my hope is that we'll be able to do it in the air. And we'll be able to demonstrate not just the instruments that are effective for that, some of the technologies like sampling technologies, whether they're claws or drills that allow us to be able to bring material back to a rover. But I really think that Ingenuity opened a completely new way of being able to explore Mars, and that we're going to see many more drones in the future. And so we've been working with a number of folks from JPL for our science helicopter concept, and there are a few different contenders. Athabasca Valles, this young volcanic terrain is one, Valles Marineris is another, polar stratigraphy is a third. We're all in a very friendly competition to be able to see where we're going to send our drones. But once you've had a chance to be able to fly, it completely changes your perspective about how to explore volcanic terrains, not just on Earth, but also on Mars. Thank you.
The switched drones change the reliability of the delivery system. I know with the the rocket lander for the ground rovers, there's a lot of stress, right? I mean,
Yeah.
something goes wrong. Would you be able to lower down to a point and then just let the drone, release the drone and let it fly off on its own and land?
So the main delivery system that allows this to is that we're limited by the diameter of the aeroshell. But we don't need to have the sky crane, because once we've done the initial aerobraking through the parachute system versus the shell, and then you have the parachute, you just drop the drone and you start the props in the air. And so you actually could use that system to be able to bypass the very expensive delivery system. And so the whole sky crane thing puts that mission tier into what's called a flagship mission. But we think we can do a drone and what cap they have. Discovery missions could be hard. New frontiers certainly possible, but the folks at JPL think that it might actually be possible to do it at discovery mission level. And the key to keeping the mission cheap is to be able to actually use the drone to land safely and not use a very expensive system like the auxiliary sky crane.
So you can get enough drag from just a parachute.
You do the aeroshell, parachute, then in the air, release the drone, turn on the props, and then it's the props that carry you the last section of the way. But you have to get to deeper and deeper sections of the atmosphere before the props will do anything, because it is still very thin.
Okay, so the atmosphere is thin enough that it's, you know, it has to slow itself down, but it's not gonna like rip the.
No, you have to do first aero braking, then parachute,
Right.
and then the very last stage is release the drone and turn on the props.
Right, but a parachute's only gonna do so much in such a thin atmosphere.
They're big parachutes and
Okay.
they're a critical first step in being able to, even with the sky crane system, you wouldn't be able to land if you're just using retro rockets from the start. So they do use parachutes as their step one.
How would you simulate the thinner atmosphere while like flying the drones around? Because I would think that that would really affect, you know, how much it can lift, and how far it can fly and everything.
Great question. So this type of research is called planetary analog research. So an analog has fidelity in some areas, but doesn't necessarily need to have fidelity in all areas. We don't care, for instance, about the overall temperatures. The temperatures in Iceland over the summer are much hotter than Iceland. On Mars. We don't really care about the pressure conditions. What we're trying to simulate in large part are two different things. The first is the technologies, but the technology we were trying to develop was drone-based sampling systems, ensuring relative navigation, which don't depend on the atmosphere. And then the other thing is we're trying to simulate the science operations concept. So how do we incorporate a workflow that allows you to have the mobility that a drone would have in a way that's effective? And so we have these papers that then present some of our insights about how to structure a mission science operations concept using drones. So we have high fidelity in terms of things like controlling bandwidth or energy. We have high fidelity in terms of imaging images that we're collecting and how we're using them, but we aren't trying to make a Mars rover. And as I alluded to before, we actually have 3 different drones that are simulating different parts in the same way that we're simulating without our robotic arm the capabilities manually, because we're trying to get some insight using the areas where the analog has high fidelity, but we're not trying to create a Mars mission and operate it in Iceland. So that's the cheat, the conceit, if you will. Yeah. Yes.
So you talked about wind eroded rock on Mars, but with so little atmosphere, does it just greatly extend the time? Or was there once more atmosphere on Mars?
Both.
Okay, where did it go?
So in terms of the higher atmospheric pressure, this would have been way back when Mars was having high enough pressure to be able to sustain liquid water and such. In terms of, and we'll come back to a moment on the question of where did it go. The other factor is time. So when we talk about young Mars, young volcanic terrains, they are still millions of years old. When we look at the sedimentary record in Jezero crater, we're dealing with billions of years. So things on Mars end up weathering very, very slowly because of the lack of liquid water and because a lot of the processes involved have different energies. And so the type of sand that's moving around on Mars is actually finer grained than it is on Earth. It carries less energy. All the erosive processes are slowed down. When the atmosphere was higher, then you would have been able to move larger grains and such. Where did the atmosphere go? Well, the sun has been bombarding, just as we talked a little bit about what happened to that ice and the permanently shadowed craters. When you have high energy particles that impinge on a water molecule, you break it apart. And Mars has a small enough gravity that while it can hold on to certain things, it can't hold on to hydrogen very well. And so the hydrogen escapes to space. The oxygen ends up interacting with things like iron on the surface, oxidizing it and effectively turning it red. And little by little, you lose the atmosphere. And one of the missions that I showed for the Mars fleet is MAVEN, which is specifically intended to be able to study the atmospheric processes, its composition, history of atmospheric escape, among other atmospheric processes.
What about all the nitrogen, or did it not have the same level of nitrogen as Earth?
Well, this is a very, very good question too. Overall, Mars is more of a CO2 dominated atmosphere. It doesn't have the same degree of nitrogen that the Earth does. Part of that is the degree of volcanic outgassing. So Earth has had far more time through volcanic cycling and plate tectonics to be able to release gases, including nitrogen. And so it's been able to build up more nitrogen. But there's a very but the whole history of Mars and the production of its atmosphere and escape of Mars's atmosphere is a very, very nuanced and interesting topic. But for the most part, when we think about the time period on Mars where people have traditionally looked for life, it was this earlier time when the atmosphere was thicker, liquid water was stable, Jezero crater would have had water sitting in it, would have been a lake. My whole paradigm for exploring Mars is that's great, but what about young volcanic Mars? All the different types of microbes that could have been adapted to living in impact-induced hydrothermal systems, living volcanically supported hydrothermal systems. What happens if we get a new eruption? Can some of those organisms, if they were present, be reanimated? And maybe we could look at some young examples of Mars and not just that old time period when the atmosphere was thicker and liquid water was stable.
So I think we should ask if there's any online questions.
Yes, I have one online question. The question is, does each researcher have their own tent?
Yes, that is why we have a lot of tents. So everybody actually had a 4-person tent with a cot and quite a bit of space. We also had the group tents, and when weather became bad, we actually got the cabin as well. But everybody had their own tents because if you want to be able to keep that many researchers happy, you get them a cook, you get them good food, and you give them a good place to be able to sleep in their privacy. It goes a long way. Mountain hardware.
Are there any last questions for Christopher?
It seems like the holy grail is to get one of these sample rockets back to Earth so we can look at it, because there would be nothing like having it here. How long until, I know it depends on political climate and blah, 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 but ballpark, how long until we might get one?
It depends on the political climate.
I mean, okay, from never to a year from now.
So this is a very good question, and I don't want to go into the politics first. So instead, I'll focus on the degree of cooperation needed. So to be able to bring back a sample requires a lot of different innovation. We need to be able to send something which can collect the different samples. We have to load them into a vehicle. We have to either land a rocket which has the propellant needed to get you back to orbit, or you need to be able to manufacture it using in situ resource utilization. If we ever send people to Mars, we're going to need to use that same type of technology to get us off the surface. You then have to have a vehicle in orbit, bring it back. That type of project would be exceptionally expensive. It is our decadal #1 priority, is to be able to bring back the samples that are being collected, but it's a joint effort with additional partners, including especially the European Space Agency. So it requires a lot of cooperation, and it requires a lot of technological innovation. And it does require a lot of money. Now, the NASA budget overall is actually very, very small. We're talking like 0.5% of GDP, and only a small fraction of that goes towards space exploration. So it really is a dial. How fast we can do it depends on some aspects of orbital dynamics. There are a couple of different transfer orbits that are a little bit better, but they've got good cadences. About 18 months is the best of them. But you can't just throw money at it. You need time to be able to solve those problems, but you need to be able to have sustained collaboration between a number of disciplines. So if we wanted to do it quickly, and we had the resources and we had the cooperation and people were behind it, it would be a very small fraction of the different budgets that work for NASA and for ESA in terms of GDP of Europe and the United States. If you were, for instance, up the fraction by 0.2%, then you could probably do it in 5 years, maybe 10 years. You know, it's that kind of time frame. If you don't have effective partnerships, then the time goes to infinity, even if you have the funding that you wanted. But really, in terms of our whole Moon to Mars system, and eventually, if you want to get people there, we have to solve the problem of how to launch from another planet, whether that planet is Mars and being able to bring back samples, or it's Mars to be able to bring back our astronauts. This is a huge innovation that's needed to be able to enable the next generation of space exploration. And so we will do it. I wouldn't bet on when, but the good news is those samples can probably sit on the surface for a while, and we'll bring them back, and we'll be very happy when we do. But this is why, if everybody is excited about this kind of mission, about the technologies and about the opportunities that people for this type of exploration, it's great to support that in whatever way you can, whether it's a phone call or whether it's coming to a meeting like this. This is a dream that we all have, to be able to explore the solar system. Part of that is to be able to bring these samples home and the technologies that are enabled by doing that.
Thank you. I think we should wrap up, but let's thank Dr. Hamilton for the talk.